Bismillahirrahmanirrahim. Welcome back to my channel. Today is going to be another video on antenna testing, and this antenna that I received, it's actually an ultra wideband antenna by a company called Deep Ace. They make different type of antennas. They make different type of devices like spectrum analyzer and VNAs and stuff like that. I ordered it from China. All of a sudden, I got this antenna. So let's check this antenna and let's see the functionality of this antenna. Since it's an ultra wideband antenna, so it should be covering a long range of frequency. So what they're claiming on their website is that it should be covering frequency range from 3.1 gigahertz all the way up to 9 gigahertz. So let's just quickly look at this antenna. This antenna is a small antenna. It's a monopole antenna. If you were to look at this particular antenna, as you can see behind this, it has a ground plane, and this is on the back. It looks like it's just the labeling of the company. All right. This is a small antenna. Why the size of an antenna is small? Always remember that frequency is inversely proportional to lambda. As the frequency will go up, your lambda will go down. Once your lambda will go down, your antenna size, which is dependent on lambda, will shrink. That's why this antenna is small. All right, mostly high frequencies antennas are small. So what is the other way we can make these antennas? We can make a array of these antennas by combining these smaller antennas together and make an array of it. So this is an ultra wideband antenna. They're claiming to be from 3.1 gigahertz all the way up to 9 gigahertz. This is how this design of an antenna looks like. I was surprised by the size actually. And I'm thinking that how much effort has been gone into designing this and then fabricating it. Of course, this is fabricated on FR4, which is the cheapest and the readily available substrate that is there to design antennas. Of course, there are substrate like Rogers and things like that, which are more expensive. All right, so let's briefly look at what should be the frequency. So this antenna is claiming to be from 3.1 gigahertz all the way up to 9 gigahertz, but FCC has a frequency spectrum from 3.1 gigahertz all the way up to 10.6 gigahertz. Of course, for Europe, it's a little bit different, but FCC regulates it should be from 3.1 all the way up to 10.6. But this antenna is claiming to be from 3.1 all the way up to 9 gigahertz. So let's just connect this to my spectrum analyzer and let's look at it. On that frequency range, what they're claiming to be, I should get a return loss up till negative 10 dB. This is what should be my return loss should be. And this antenna should be good enough for an application that it can handle up to 5 watts of power. That's what they're claiming this to be, that this antenna will be able to handle up to 5 watts of 5 watts of power. So I'll be unable to calculate the power and also the gain, because in order to calculate gain and radiation pattern, I need to check this antenna in anechoic chamber, which I don't have available. So let's look at my VNA. What does the graph says? All right, by just first hand looking at a graph, it looks good, because I think this starting from this point to this point, this should be the resonance frequency, because this is my negative 10 dB line. So from this point all the way up to here, this should be the resonance, because this is below negative 10 dB. So let's look at it. Let's call in our markers first. So let's look at it, bring our markers, and let's move this. All right, so they were claiming that it should be operating from 3.1 gigahertz all the way up to 9. So if you were to look at these values, 3.1 is right here, and it's no way negative 10 dB. It's not 10 dB. Return loss is not 10 dB. It's actually below that. So this is not good. So the matching at 3.1 gigahertz is really bad. All right, let's bring in another marker. Where does this antenna start resonating where I get negative 10 dB? It's about this point. So let's bring our marker here. Let's call in our another marker. So let's go at this point. So at about 3.9 gigahertz, I start getting about negative 12 dB of return loss, which is good. So let's look at different peaks that I'm getting. So let's call in marker 3, and let's look at this third peak right here. This is at around 4.7 gig. I can use this antenna from anything below negative 10 dB. I can use this antenna on this line. I can use that easily. But I'm just focusing on the peak so I can bring in my markers. Let's look at marker number 4. Let's quickly go to this peak. Alrighty, let's look at this. So this is around 5.73 gigahertz. This is good. Let's look at a band. Let's look at another peak. So let's call in peak marker 5. Let's just simply move this marker over here. So at around 5.8 gigahertz band, which is actually a Wi-Fi band, this antenna is also looking good. So this is around 5.8 gigahertz. So at 5.8 gigahertz, I can use this antenna for Wi-Fi application as well. But I'm just going to focus on the peaks. So this is around at 6 gigahertz. So let's look at peak marker number 6. Quickly move to these peaks. Just this one, and then let's just call in another marker. So marker 6 at about 6.3 gigahertz is good. I'm going to go and bring another marker at this point quickly. Probably I need to. So marker 7 is about this point. That's 7.6 gigahertz. All right, so my this antenna, as they're claiming, from 3.1 gigahertz all the way up to 9 gigahertz, but my VNA that I'm using, it goes from 100 kilohertz all the way up to 8.5 gigahertz. But as you can see, as the frequency is going up and up, I have this is no more negative 10 dB. It's going up, as you can clearly see from this point. So right here is going up. So I'm just going to bring one more marker, and I'm going to bring one here quickly, just to show you marker 8, which would be this point. So this is at about negative 9. So 8.3 gigahertz, this is at about negative 9 dB. This is what I'm seeing. All right, one other thing that I want to look at, let's look at our SWRs. So let's bring in another measurement, and let's look at the ratio. Let's go to S parameter, and let's look at the format, and let's look at SWR. All right, so these are the SWR values. All right, before I show you, let me explain what SWR is. Standing wave ratio. All right, once you know your return losses, you can easily once you know your reflection coefficient, and you take that reflection coefficient, negative 20 dB of negative 20 log of your reflection coefficient will give you return loss. So reflection coefficient, they are actually relatable things. So this is a plot for an SWR for an antenna. An SWR basically means that, okay, what is the rule of thumb for SWR? As long as you have an SWR of 2 when you're designing these RF equipment, either the entire communication system or either a component or either an amplifier and antenna, as long as your SWR is at around 2, which is good, which means SWR being 2 means that 50% of the power is being absorbed by my load. That's what SWR, having an SWR of 2 means, that 50% of the power is being absorbed, which is being received by my load. Either it could be an antenna, it could be another device, and 50% is being reflected back. So when we're designing these equipment or these components for RF application, I want to make sure my SWR is below 2. So as we can clearly see, at 3.1 gigahertz, we were not getting a good return loss. Hence, we have a higher SWR, which is at around 2.69 gigahertz. But on the other places, everything is below 1.6, 1.3, 1.1, which is very good. 1.1 is very, very good. 1.09 is very good. So these are good good SWR values. You know what? I'm going to bring in my so this one is SWR. So let's display, and let's look at a diagram, and let's add a diagram and a trace. Okay, I can look at it like this, so you can clearly see. All right, let me change this measurement. Measure. This one is showing S21. There's nothing connected to S21, so let's just change this to S11. Okay, so this is S11, and this is an SWR graph. You know what? Let me change this. I wanna actually look at this in terms of a figure display. All right, let's split this, and let's split them vertically. So let's split. All right, and let's do them vertical. Okay, now here we can see. I can clearly see. So now this is an SWR plot, and this is an S11 plot. So these, every single marker is being represented in terms of frequency in SWR, and this is what an S11 graph with return loss on the vertical axis. You can see this, and this on SWR, the plot is still frequency on horizontal axis, but here you have values in terms of linear numbers like 1, 2, 3, 4, 5, 6, 7, 8, and all of this. So anything that is less than 2 in terms of SWR is good for any RF devices. And anything less than negative 10 dB in terms of return loss, which means it's a perfectly matched device, which is good. It will work perfectly fine. There's everything is being most of the time being absorbed by my load. So I hope you like this small video. I was actually surprised. I hardly pay. I mean, it was like around $3 for this antenna, and I was just thinking that in order for me to design this antenna and to get this antenna fabricated to do exactly the same task, I mean, it requires a time, money, and everything, and all the resources. You know how hard it is. If I were to design this antenna on in CST microwave studios or ADS and Momentum and things like that, and then plus to get fabricated, wow. For $3 you're getting an amazing device. So if you have any questions, leave it in a comment section, and don't forget to like and subscribe to my channel.